All right, let's get started. So today we're going to talk about forecasting methods. Again, same type of thing as last time. We're doing these sort of higher level highlights of approaches. There are, again, sort of classes that you can take specifically to elements of methods that we'll talk about today. All right. Where's my mouse? Here we go. Forecasting. So this is the process of making predictions based on both past and present data. So I've got two sort of forecasts over here that are done in actually very sort of different ways, even though they're both from the EIA, the Energy Information Administration. On the left, you can see sort of power sector generation, right? And you have historical data on how much power is getting generated from, say, renewables versus hydro versus nuclear and so on and so forth. And that goes, so this was back in 2019. And you can see past that point that they actually do sort of forecasts, right? And so this would be a sort of short-term forecast. And so you do have differences in types of forecasts based off of the sort of length of time that you're looking at, right? So the scope can help determine the approach that you end up taking. In this case, this might be some kind of simple sort of extrapolation, right? On the right-hand side, you have sort of projections going sort of all the way out to several decades in the future. And one thing that you'll sort of note about what happens once you're in your sort of projection world is that a lot of this sort of, well, kind of noise, which it's not actually noise, but right, so some of these artifacts are smoothed out when you're doing some of these longer term forecasts. And we'll talk about sort of why that is depending on what sort of forecasting methods that you're using. So again, the approach that you take is going to depend on the type of forecast that you're doing. And then we're going to talk about what sort of differences and assumptions that you'd be making between these different types of forecasts. So then, yeah, so I'll maybe pose the question. So what forecast do you think is more or less certain? Which one has higher uncertainty? The longer term one, right? And so as you think about doing sort of longer term forecasts, you can think back to some of the like sensitivity or scenario or uncertainty analysis that we had covered in previous lectures, right? And think about the application of that to certain types of forecasts as well. The dependency of forecasts on, oh, let me move this thing up here. All right, so the dependency of forecasts on your current or present, your present and past data means that your forecast can change, right? As you update information about what has happened in sort of the recent past. And so this is actually a demonstration of how different that can look with just a 1-year difference. So these were two forecasts done by Bloomberg NEF, projecting out electric vehicle adoptions and their model using 2015 forecasts versus their model using 2016 data. And so, yeah, so one of the big things to remember here is, right, especially for newer technologies that are coming into the market, if you're like forecasting adoption, there is substantially more uncertainty, and that you should think carefully about trying to avoid, this kind of just level of discrepancy when possible. It's not always possible, but and we can see another kind of interesting example of this. So, kind of as evidenced by the last slides, forecasting is hard. So these are natural gas prices. So the EIA publishes this annual energy outlook, which is a sort of large-scale modeling exercise that they do to project forecasts of the energy system in the United States. And that includes sort of technical aspects of it as well as economic aspects. So here, in this chart here, these are projections of natural gas prices. And each of these lines represent the 2004 forecast, the 2005 forecast, the 2006 forecast, and so on and so forth. And you can see the actual price of gas going in 2009, and you can actually see what that is over here. This is kind of adjusted to be the same scale. And so whereas all of these forecasts are all, starting in 2009, $5, $5 per MMBTU and up, you can see that actually almost never happens up until very recently. And so you go back and you sort of adjust your forecasts with new data as possible when possible, but especially for things that have a lot of variability, forecasting can be very difficult. And so these retrospective looks at the outcomes of forecast models that people have done is always kind of interesting to see how close or how different they get to reality. Any questions about this? All right. So different methods to do forecasting. So generally, there's these three categories. You got time series methods, which are sort of trend analyses, econometric. I might even separate econometric and predictive forecasts, which generally are done by sort of machine learning algorithms. So these are more structural analyses where you're trying to look at relationships between things that explain certain outcomes. And we're not really going to talk about this one today, but the other method of forecast is to do like simulation of end-use services. So this is sort of particularly for energy systems modeling, where you're sort of building out from the ground up as opposed to looking at sort of macro variables to do forecasts. So within time series methods, again, we're not going to totally cover everything that that would be encompassed under time series, right? So you can actually take entire courses just on the series of methods here, but we will look at some of the general models and categories of models that are used here. So regression-based models, decomposition models, exponential smoothing, and then Arima models. It's kind of weird to categorize these actually because like the first two are kind of subsets of this one, but yeah, but it's one way to show sort of different sets of models in time series. And then for econometric approaches, we'll talk about some generalized methods, and we'll talk a little bit more specifically about examples of specific structural or structured regressions that people have used in the area of forecasts.
When you say structural, it means like more layers, or
no, so
like economical, social,
no, so what I mean is in time series methods, it's like you are looking at patterns, whereas in econometric models, you are looking at relationships between variables. So that's kind of what I mean by structural. Okay. So in order to get into some of this, I'm going to do a quick primer on regression. So again, this topic in itself should be covered in almost its own set of classes or several classes. But for those who are sort of less familiar with this sort of modeling approach, we'll kind of cover some of the basics here. So this is a statistical process for understanding the relationship between variables given data about the variables. So let me do a quick example. So let's say you have some set of data, X's and Y's, and you want to understand the relationship between X and Y. And let's see, I have some set of points like this. And so you may have heard of something like a best fit line. So maybe that might be a line that looks like this. Conversely, maybe I could draw a line like this. A line like that. And maybe a line like this. Okay, so then raise your hand if you think the yellow line is the best line. The green line, the red line, blue line, couple people. Okay, so then, all right, so let me get rid of these two because these were very unpopular. So how could I, so, okay, eyeballing it, maybe you get a general sense of it, but then how could I actually tell quantitatively which line is better? Yes.
I think you could take the distance between each point in the line and then, I don't know, sum it up or square it and take square, like do something with them and
Yeah.
see which distance is lower.
Yeah, that's exactly right. So I can look at these. Nope. Hang on. Come back. There you go. I can look at the distance of each point to my line like this, and I can compare the distance, right, of each of these. Yeah, so that process you're describing, if you sum up the square of the distances, and so actually, why do we square it? Yeah.
Some values can be negative.
Yeah, exactly. So then they would like cancel out, right? Yeah, and so actually, do you know why we square it and we don't take the absolute value? Pop quiz, anyone know?
the relative rankings are gonna be the same, whether it's square value or not.
Yeah, but in practice, we do OLS, which is ordinary least squared, and we don't do ordinary absolute differences. Yeah, so so you're right in a sense that actually it wouldn't necessarily make a difference. It actually does makes the estimation slightly different. But our choice to do squares is actually because computationally it's easier. So before you had computers and you have to write it out and you have to solve these things by hand, your ability to do an analytical solution is much easier with squares versus absolute values. So that's a little bit of trivia in case anyone ever asks you on a trivia night. Okay, so where was I? Yeah, so I can look at the square of the difference for any point, and I can add it all up, and I have some metric that basically tells me how wrong I am. And you can do that for the red line, and you could do that for the blue line, and whichever one has that smaller error term would be a better line, right? So what is the, so okay, let me get rid of, oops. Let me get rid of the blue line. So then what is the equation of a line? Mx plus b, right? So y equals mx plus b. So this describes the slope, and this describes the intercept of the line. And then what I'll just quickly sort of comment that generically, we actually, it is the common notation for this in econometrics, uses betas to describe your slope. So sometimes you'll have something like this. You can also have like beta x plus alpha is also common. But again, this is the same thing describing the slope and the intercept. Yeah.
You also have the intercept at the end?
Yeah. All right, here, there, you happy? No. Yeah. Yeah, a little bit more about the notation. So this little hat indicates a predicted value. So you will have you only have the error term here to account for, oh sorry, without the hat, to account for the differences between your prediction for any individual point. So it would be, so you would have this equation, and then you would have this equation. And the difference being this error term letting you get to the actual value of yi as opposed to the yi hat, which is the predicted value. So that is the point on the line. So in other words, if this was, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if this is x9, the point corresponding to here would be y9 hat, and the y point corresponding to this would be y9. Okay, does everyone understand the difference? Okay, so backing up a little bit, right? The whole idea is that you can describe relationships between your X variable and your Y variable based off of this sort of correlation that you're deriving from the relationship that you see in the data. And so that's one of the most fundamental tools that you can leverage in data analysis and in these forecast models, is trying to get a sense of relationships between these variables. Any questions about this? Okay, so in a linear regression, you can actually have sort of more than one relationship to your outcome variable. So just some more nomenclature. So Y is your outcome. This can be called a dependent variable, which is commonly what you'll see in like econometrics. I think it's actually a bad term. So we're going to call it a response variable, explanatory variable, which would also commonly be called an independent variable. The slopes are described as coefficients. And so these describe the effect of the explanatory variable. And so it's actually exactly, you know, that slope term, right? That's being described by this beta. And the interpretation of it is actually really sort of nice and convenient. And we're going to talk about, as we sort of stray away from sort of linear approaches, how that gets a little bit more convoluted. But in this case, you know, as I change x2 by 1 unit, that means that y changes by beta 2, right? And so the interpretation of it is actually one of the big reasons why, you know, linear regression continues to be so widely used. And then there's the sort of error term. So this would be stuff that you're not capturing directly, and that can lead to sort of noise in your model. Yeah.
Is the constant offset captured by the error, or by one of those xm being a constant?
Wait, sorry, say that again?
It's a constant offset, like, you know, you're in mx plus b, the b.
The intercept.
That's beta naught, right?
Yeah. So you could have an additional term here, beta naught. So this would be your intercept. Yeah, you don't always have to have an intercept. So an LS, so this stands for ordinary least squares. And that is essentially what is being used to solve the coefficients. So actually, if you recall what I was just saying, we have our points like this, and then we have our line, and then you want to get the smallest difference. Going back to our lecture from Monday, this is actually an optimization problem, okay? And your decision variable is the slope. So your decision variable is like, oh, should I draw a line here? Or should I draw a line here? Or should I draw a line here? Right? And so it is picking the line that minimizes the least squares measure of your error. And that is a well-known enough of a optimization problem that it's been solved. So you have like analytical methods to solve this particular optimization problem. Okay. Any questions about that? Cool. All right. So let's move on to talking about our first category. So time series methods.
To close the regression, so I have the data.
Yes.
And there's probably somewhere I think I will draw best fit lines, and I can say I want or 7, and then I have to do the process to do the test.
Wait, what do you mean 3 or 7?
Yeah, right now it's logical, like it's all the points. This would be. Like this slope of the line.
Yes.
In the computer, how do you do it?
Yeah, okay, so to actually solve a regression, what that means is that you are figuring out what all of your slopes are, essentially, your betas, your coefficients. And so there's lots of different types of software that can essentially figure that out for you. It's essentially running an optimization. So if you want to know, yeah.
You draw a line, and then you calculate the distance.
So yes, except that you wouldn't actually draw the line manually, right? Because you wouldn't be able to know which line is best, and you wouldn't be able to test like an infinite number of lines to try and get to the right answer, right? So the computer will solve it in one of 2 ways. It'll either do a gradient descent algorithm, which is right, one of the ways that you can solve an optimization. So you'll do that in machine learning contexts, but more commonly for smaller format problems, the closed form solution for beta. Does everyone know this off the top of their head? And then ytx, right? Something like that. I see you writing this down, but I don't actually know if that's completely right.
Actually, it is like the hot matrix times y, and you have to
It's xtx minus, it's the inverse of xtx is the hat matrix. Oh, so there's no x at the end. Right. Wait, is that right? Like this? I feel like this isn't quite right.
So if I can do a package, you say, give me
x
linear regression.
Xt, right? Somewhere. Yeah, that's what, yeah. I was close, okay? It's x, yeah, that's it. So, okay, so, yeah, so this equation will solve the betas for you, just straight up, okay? But this is kind of the, and you can, there's like math behind how to derive this. So if you take a like introduction to like a regressions class, you would learn how this is derived. And this matrix operation allows you to derive beta for any generic set of data inputs here.
That would go in.
This will give your beta, which is what you would, is the slope of the line. Yeah.
I'm guessing it gets real complicated real fast, but is there an equivalent for that has crossover terms as a beta matrix as opposed to a list? So, you know, beta 1, 2, beta 1, 3.
No, this is, oh wait, what? What is that?
Yeah, probably.
Yeah, this work, this is a matrix. So this will give you, this will,
It's just diagonal.
the element, but it is gonna result in a column.
yeah, so this gives you a vector of betas. So this generically can be used to solve any number of betas.
Right, I'm just wondering about, it wouldn't be in the form, you know, y is, it doesn't matter, it'd be a different type of regression.
Yeah. So this is specifically for a linear regression. So then the thing, so even though this, like, it's a super easy equation and it's fairly straightforward to solve. So the reason why in machine learning you don't do this is because this term right here is a very memory intensive dense matrix. So once you are operating with, let's say, 1,000,000 data points, that can crash your computer, right? It might be either crash your computer or it'll take a long time to compute, because doing the inverse of such a large matrix is actually fairly computationally intensive. So even though you get this like perfect solution, closed form analytical method, yeah, you actually go back to a numerical method once your problem is big enough.
I guess I was wondering, is there other closed form solutions for regressions that take into account variables that depend on one another, that are non-independent?
You have to check for multi-collinearity though. Like if
Yeah, so
any of the explanators are collinear.
yes, okay. I'm gonna say, so generically, not specifically in reference to your question about independence of your explanatory variables. So there are lots of different types of regressions, and the set of regressions that you can solve with analytical solutions is actually relatively small. Basically, the more complicated they get, like the less likely that someone's developed an analytical solution for them. That someone has developed a like closed form solution, right? Usually you have to run through some numerical method. Okay, but let me sort of get us back on track here. What I'll say is that if you want to learn more about this stuff, you should take a class. Yeah, because you know, for this particular class that's trying to cover like a host of different tools, you know, it's always a challenge for me on like, what do we actually cover, and how much detail can we get into in any particular thing. So yeah, what I would say is like, as you the most important thing to take away from all of this are like the principles, right, of understanding like what a regression is trying to do. And then in terms of like the actual solving of the regression, you can leave that to the computer.
Yeah, more like high level. I plug in the values of X and Y for the data given
Yes.
into an equation that I'm going to choose based on, is this our structure,
Yes.
relationship, or
Exactly.
or pattern?
Exactly. So so with this, the structure is like a linear structure, and we'll talk about other structures too, and possibly how to solve them. Okay. So time series methods. You know, I take these like formal definitions from the internet, and they all kind of look the same, right? We use past concurrent data to predict future values. So maybe I'll put a more specific spin on it. So like time series is specifically concerned with data points over time. And so what you're going to find is that those X's in regression, so we're going to talk about some regression models specifically in time series, a lot of the X's are just your previous outputs time period. Okay, so what does that mean? So a classic example of this is where you use time varying processes as your explanatory variables. So we care about some outcome xt, and that is dependent on xt minus 1. So whereas, so the sort of specific difference, right, is that let's suppose you wanted to do more of an econometric approach, and I wanted to look at like GDP, for example. in each time period. And you might say that, oh, I have information about unemployment in a particular time period. So the way that you are estimating the strength of the economy is based off of its relationship to current unemployment rates, right? So what autoregression does is it's not looking at the relationships, it cares about the trends happening with GDP over time. So instead of this, you might say, well, let me get a prediction of what GDP is based on, given what we saw last year and the year before, and so on and so forth. So this is actually a fairly simple but powerful way of being able to capture time trends, right? And so the number of years that you go back is described by this P right here. We're going from 1 year back all the way to P years back. So that's the number of time lags that you capture. And then you can sort of build forward off of that. If I were to predict this value, I can then use that value to input to find t plus 1, and then t plus 2, and then t plus 3, and so on and so forth. And this lets you capture even sort of fairly nonlinear trends that might look something like this. Okay. There's no L, but the I refers to your time period. So okay, so forget about the equation for a second. So do you understand this? So you have t minus 1, t minus 2. So your GDP depends on last period plus the period 2 periods before. All that's essentially what your I is saying is the period. Yeah, so you have a dependency on your previous periods. Yes.
For the error term, is this, that can be just a calculated number from a separate formula, whatever you want to add in there, right? If you're using GDP as an example, something that could impact GDP that's not based on GDP could be.
No, well, the error term isn't something that you would like discretely. It's not like a constant, right? So the error term, huh? Yeah. No, so the best way to think about this, so let's see. Let's say yeah, let's say you have something like this, and then your model lets you predict something like this. The error term is just the difference at any time point that represents the difference between the true value and the predicted value.
Right, no, I understand that, but if you haven't made the prediction yet, like you get the error term afterwards then, is it generated afterwards?
Yeah, so, I see what you're saying. This, so then really, really the,
it's xt minus the error, and then it gives you your prediction. But
yeah, so,
it
yeah, so if you wanted to figure it out, it would be xt minus xt equals that. Yeah. Or xt minus xt hat. I forget which one comes first. I think it's the xt comes first, so it should be, do this properly. It should be this xt minus xt hat equals that. Yeah.
It's trying to minimize some of those error terms, the deviations after determining those betas. So determining the sort of the impact on the predicted variable of each of these previous values, and then minimizing that, square of that. Is that what's happening?
Yeah. Oh, are you asking if this is like just a linear regression? Yes, it is. So it's linear in terms, right? And you're using the structure to describe a nonlinear relationship, but it's still a linear in terms, linear in parameters. Yeah.
Do those betas with any frame of the time series of the time,
It's actually, I mean, it's still, so it's describing the relationship between each time period and the current time period of interest. So for example, let's say your GDP is always double last year's, and then let's say it's always quadruple 2 years ago. So then your beta would describe exactly that relationship, that it would be like 2xt minus 1 and 4xt minus 2. Yeah. Yes.
So this just so I got this forecasted value. So you from this your actuals and then the predicted, you have your errors, whatever it is, and then if you're like on a forecast,
Yes.
then you just use that error term. Right? So you back cast first, find the error, and then you use that as your basis for forecast.
No, because in your forecast, you're dealing with xt like this. So you wouldn't have a error term here. It would be like this. I, P, beta I, xt minus I, like that. And there's no.
Yeah, I guess I'm asking. I guess I'm asking when you're trying to do the forecast.
Yes.
And you're trying to find.
Yeah. So you take this and you put it in as a prediction into your next ones. And so you're actually pointing out a like fundamental problem, which is, okay, so this error term represents how far off you are from your prediction. So imagine, so when you forecast outwards, like you don't have any information on what's actually happening to be able to calculate an error term. And so the fundamental assumption in doing the forecast is that the sort of mean of all of your error terms is going to be 0, right? But if it's systematically biased, then the more you forecast and you haven't included your error term, which you don't know, it's like an unknowable thing, then the more like incorrect your forecast is going to be.
Yeah. I'm trying to get at how you would tune. Maybe this is the wrong model in which you would like tune your forecast based on expected growth rates or expected adoption rates of EV such that it influences that, right?
So again, so think of like time series as strictly just looking at trend data, essentially. And so it's like really good at figuring out trends, but then if you ever depart from your trend in any way, and you haven't established some kind of like measurable relationship, then it's only going to go so far, right?
But then once you find it, you forecast in the next 3 years, you realize that I was wrong.
Yeah.
Right, I'm gonna go readjust based on what
Yeah. So, this is like the level 1 complexity for some of these time series modeling. And so there are ways that you want to move beyond just doing these lag terms to try and capture stuff that might be contained in your noise, right? And so we will look at some of that. Do you have a question? Yeah.
When you do time series, you need to decide how many lags we are considering.
Yes.
Should we consider?
Yeah, good question. So, yes. So the short answer is yes. So the principle here is actually, I can actually include as many lag terms as I want, right? And the more lag terms that I get, actually, the closer you will always be closer to your true value as you put in more lags. And that's because you're essentially working with more information. But that does become problematic. And does anyone know why? So,
Have weird outliers.
close. Maybe this. Okay. The concept is basically this. So let's say this is the best line that you could do with an OLS. Can you think of a line that would beat the OLS for doing predictions? Yeah, in fact, I can do this. And now my error term for these lines is 0. So it's like way outperforming an OLS in terms of the points that you see here. In fact, let me do another even. Okay, right? Like I could do that and it would be better. Does anyone know what this is called? This is overfitting. Okay. So the idea is that as soon as let's say I left one point out and I put it back in and I tested it against, so you're essentially testing your model against data that you didn't train it on. So the more complexity that you add to the model, AKA the more variables or the more lag terms that I add, the more likely you are to be sort of overfitting the data. So it's a trade-off between bias and variance. It's a trade-off between like doing this squiggly thing versus like a generic, like a random line. And you want to find the sweet spot. And the way that you find the sweet spot is by doing out-of-sample testing. So yes, this goes like way beyond what I wanted to cover. But what I'll say is that the choice of lags, there are like metrics and tests that you can do to figure out like how to balance the overfitting part of it. Yeah.
The overfitting, apologies, this is like basic steps on this. Like overfitting is because it's not representative of what actually, like doing this is not a real thing that happens in the world, in the real world. So you try to pick the fit that is more reflective.
Yeah, but the only way that you could know that from like a statistical perspective is by like testing your model against data that was not trained on. Yeah.
From there,
Mm-hmm.
GDP is a good example because it's happened for many decades.
Yes.
And you can see the trends in the past, like people miss it by this much often.
Mm-hmm.
Does it help to use that at all?
Wait, help to use what?
Past error and calculating future GDP?
Yeah, so basically, I mean, it's kind of a similar question that he was asking. Like your error term is entirely driven by whether or not there's like a trend that is so in the context of autoregression, your error term will be entirely determined by how clear of a time trend that you can derive from the data. And so, GDP happens to be a nice example because it's fairly-ish stable, so that you can like figure out the trends reasonably well. But if you're doing like totally random things over the years, then this will do less well. Yeah, and so it is connected to how much data you have, but it's also connected to like what the trend actually looks like.
The political poll analyzer will use, I assume error terms to apply a house effect to different poll providers. So they know that the Washington Post skews liberal and add an error term. The Wall Street Journal skews conservative.
Yeah, kind of. But I mean, they're all using slightly different models. So yeah, I don't know too much about the exact models that they're using. Yeah.
Does it fail in case of when data trend, the sample trend is more of a random walk? Let's say stock market volatility or oil price volatility. And you could try all you want to fit a trend line through that, but that is not going to be matching up because the nature of the way these things evolve is a more random walk in the park than the one where previous year's values are somehow linked to next year's values.
Yeah, it's possible. That's definitely possible.
Which sort of data do you recommend against using your regression model? Because the nature of data. Temperature is fairly consistent because we can find sort of climate consistency across it.
I mean, even in with random walks, if you have a sense of what the trend looks like, I mean, the whole idea with like random walks is that yeah, you start to systematically stray from your error terms tends to systematically go in certain directions, which is why, I mean, yeah, it might be harder to do with something like this. Okay, all right, we gotta move on though. Okay. This is a different type of model, decomposition model, so moving average. So conceptually, it's actually a subset of a linear regression, although I think that's like a weird way to kind of frame it. So there's an easier way to sort of understand what's happening here. So this moving average actually is a type of smoothing model, and you can kind of see that here. Here's the kind of like math behind it, but it's a lot easier than it looks. Essentially, if I wanted to, let's say, predict a point right here, all you're doing is you're looking at for a 7-day moving average, you're looking at the week surrounding your point of interest, and you average that, and that gives you your predicted value for any sort of time point. Yes. Right. This is many years ago. Everyone is. Yeah. Right.
Many is more than one, sure.
True. This could be anything. Like, we don't have to.
Well, you could just black it out.
Right.
Redacted.
But the idea, right, the concept, you can see kind of how this gives you a general prediction of what's happening, but it's washing out some of the variability. And so if that is kind of what you care about, right, this is a type of analysis that you can do. And it's a pretty easy, straightforward type of approach. Yeah.
It's like an iterative process. That trend line that's going through changes based on the next data point. So it's got a 7-day average before, and the next data point sort of changes it again and again, iteratively, until you have a full trend line. Is that what's happening?
It's not iterative, right? Because you can like calculate everything in a single process.
But you're doing it based on what happened before, so 7-day average it's coming, so
Oh, you're talking about for
Yeah.
for a forecast.
Yeah.
Yes, that's right. So, yeah. So using this as a forecast, you would have to do some kind of like iterative process. Yes.
Is the seasonal adjustment like kind of number?
Yes. So, I mean, there's actually specific smoothing models that account for seasonality that do it slightly differently, but in principle, it's essentially trying to do what a moving average is doing. That's right. So there are, yeah, definitely more complex sets of these time series forecast models. And if this is where your interests lie, definitely encourage you to look into this. So exponential smoothing models, these are particularly trying to look at some of those trends and seasonality. And then Arima models are kind of taking some of it's increasing some of the complexity of things like autoregression and moving averages and combining them to get sort of the best benefits and minimize some of the drawbacks that I was talking about associated with those models. So like an Arima model is an autoregressive, what does the I stand for? Integrated something, moving average. So it's a combination essentially of your autoregression model and your moving average model. And there are like many sort of variations and yes, slightly higher complexity versions of Arima that let you do trend forecasting, right, with higher specificity, and that do like a better job at understanding trends and relationships. Okay. So our second category is thinking about econometric forecasts. So we kind of need to shift our thinking here. It's still using regression techniques, but it's more focused on looking at relationships. So yeah, attempting to quantify relationships between your parameter of interest, your dependent/response variable, and a number of factors, which would be your independent or explanatory variables that would affect it. And so in this case, right, so we have GDP and you have your data on GDP, and then you could build, for example, a trend line here that might look something like this, right? And so the time series is really, trying to build that sort of prediction. But with the econometric modeling, we also care a lot about this type of thing. So this is a table that tells you essentially, your GDP is equal to beta of some variable. So this might be your time variable here. And it is describing, this would be beta 0, right? So it is describing the actual quantitative relationships between time and GDP in order to be able to get that forecast. So the big difference, right, is that with time series where you're generating these forecasts based off of the trends, in this case, let's say you have a good idea of the explanatory factors going out into the future. You can then leverage the relationship between that and the outcome that you're interested in to actually build your forecast. So one thing to be really careful about is that is in the interpretation of your coefficient or your slope, right? Which would describe the relationship between your sort of your x and your y. So to give an example of this, we have two variables here that are sort of really closely correlated. We can see over time, some set of values here, some set of values for, let's say for your first variable, and look how closely they are aligned over time. And so you might think that there is some kind of sort of close relationship between these two variables. But in reality, they're really don't have anything to do with each other. So this is the whole correlation is not causation, right? Unless you think that somehow people get depressed when NASA gets funding. I don't know. Yeah, so correlation does not equal causation. And the ability to actually determine causality is actually a fairly difficult problem. And that is something that is the focus of a lot of econometrics. So I'm kind of trying to get at somewhat of a theme here. A lot of the time series forecasting is mainly focused on prediction. And so really you care about outcomes based on specific values of input variables. So in other words, what is the value of y given x? For causality, so this is known as causal inference, determining those relationships. You care primarily about how outcomes change as a result of some kind of treatment or intervention in your input variable. So what happens to y when you change x? And so that's a really important distinction, and this actually drives a lot of the decision making behind sort of model choice and yeah, kind of the approach that you take. So as I was kind of mentioning before, with linear regression, it's actually a very convenient way to think about inference because the interpretability is so much easier. So it's somewhat of a generalization, right? We tend to favor this type of thing to conduct causal inference. The results are more interpretable and relationships are easier to describe. So this is a regression table. So let me go get into this a little bit. So this describes a study that was looking at the registration of electric vehicles, and they were particularly interested in understanding how, let's say, if I offered an incentive to a buyer of an electric vehicle, how that might get people to buy more EVs. So if you have something like sales over time and across different regions, one of the ways that you could, not sales. One of the ways that you might think this would get affected would be like a tax credit. And then maybe have sort of a bunch of other things, right? And so how do you know that if I offered a tax credit that it's changing sales in a certain way and it's not coming from something else, right? You need to have all these other sets of controls, and you want to be able to tell this relationship directly without any other sort of confounding variables, right? And so that process in itself can be fairly complex, and so in this particular model, there's been sort of a bunch of work that has gone into trying to determine that. And so you can interpret these numbers kind of in the same way as we did before to look at the relationship between like sales of electric vehicles and what would happen as you have some kind of intervention with a policy. So, okay, back up for a second. So why are we talking about this? So the idea is that the context of the problem that you're trying to solve is dictating kind of the approach that we're taking, right? And so I could, for example, just do like a time series analysis to look at electric vehicle adoptions, right? That would be a perfectly legitimate way of doing it, doing a forecast. But if you wanted to do a forecast for like a policymaker and they're considering introducing like an incentive, right? Your ability to do that forecast with a time series doesn't really make sense, because now you're introducing this like totally different mechanism that might affect the trend in ways that you don't have the ability to observe that before. And so if you were to do causal inference and determine relationships between like certain types of interventions, then you would be able to, let's say, do that kind of forecast. Does everyone follow along? Yeah.
Is the threshold of causality, is that to satisfy all the Gauss-Markov assumptions that come with this, that the areas of the error term is not linked?
Oh yeah, we're definitely not going to get into that. So okay.
How do you call causal? Then how do you describe?
So there are like you're saying, there are lots of like tests and yeah, there's lots of different tests and like both quantitative and qualitative means of basically deciding that the relationship is causal. Yeah, and so what you're mentioning is like one particular type of test that's testing for one particular thing, but
I'm saying all sorts of the other tests for other assumptions, so committed variable bias and all that.
yeah, you gotta cover all that, right? So doing causal inference is hard.
So in a paper, you don't say that X is causally linked to Y, or do you say that this is a suggested link? How do you claim you run regression, but then what's the use if you can't claim causality?
No, you can, but you have to demonstrate it in certain ways. So in this paper, I would say, you know, we did all this is the paper I wrote. I would say that yes, it is causal because we've done some like instrumental variable analysis. We've looked at all these tests, and we're fairly confident, given all the tests that we did, that there is this real sort of relationship. Wait, I saw a hand there first.
I was just going to say, like, you can say exactly what your model was accounted for based on that.
Yes.
Not based on everything, based on like what.
Yeah, exactly.
So for the concepts, given if we use the sort of model of linear regression, would the idea be to effectively account for all the other variables and to subtract them out of the model, leaving you with just the explanatory variable interest?
Yeah, there's a couple different strategies to determine causality. Okay, so the most common one that people do is called no, is using instrumental variable. So the idea is that you have an outcome, and then you want to determine whether or not this this x variable is related to it, right? But then you could have some kind of error that this might be like other sets of variables that aren't in your model, and you don't know if it was like changes in here that led to it compared to this variable itself. So the whole idea is that you would want an instrumental variable that has no relationship here, and that can only change your outcome variable through its relationship with x, like that. So that's the like concept. So there are all these, so again, backing up a little bit, like there are all these other sort of variations of this, and then there's like tests. So like this part is usually the hardest part, is determining that there's no relationship there, and that there's also no relationship like this. So like if you take any econ class or any econometrics class, a lot of what you'll be covering is this type of thing, because they're sort of centrally focused. There are a lot of what they do is centrally focused on this. So that's all I'll say for causality. So I think a lot of what you guys are asking about is the determination of causality, which is a complex thing and would require more than I can teach in this lecture. But what I'm trying to get, the takeaway here is that that there is a sort of fundamental difference in your decision to use these types of models versus the predictive types of models. And the context of what you're trying to do is what should determine your approach. Yeah, and so these types of things are actually more related to some of the time series things. So as you stray away from doing like linear relationship in your parameters, you are allowing for more structural flexibility. And so, as a super like generalized example, like that might be the difference between your OLS estimate that looks something like this versus like a kernel estimate that looks something like this. You get a lot more flexibility, and your ability to predict outcomes almost always improves when you are increasing like flexibility into your model. But that isn't to say that like this is necessarily better than this, right? Because if I wanted to determine the relationship, like a general relationship between my x and my y, I could not describe that relationship here, right? Because it's just very specific to what the data looks like. As opposed to here, I can say, oh, there's like this negative downward trend, right? Yeah, and so you've got series of different non-parametric models, and the big struggle with these types of things is like the overfitting part of it. And so there's techniques to avoid that, right? But again, going back to why we do these things, as you do specific types of forecasts, the reason and what you're trying to accomplish from the forecast is going to dictate what types of models are being chosen. Okay. So the last thing that we're going to cover today are a couple of examples of regression models that are actually built off of a fundamental understanding of kind of trends or sort of relationships that we know have essentially a certain shape in reality. And because of that, they have sort of like specific like structural forms for your regression. So this is a fairly simple one. So this is a concept known as learning by doing. So this is a learning curve. It's also called an experience curve. So this is an economic concept, right, that basically says your productivity sort of increases as you make more of whatever product that you're making. And that's because you have increased efficiency, both for your organization and individual. And so you can think of it like if I were building a car, for example, the first time that you do it, it's like fairly complicated, but then you get more experience building the car as time goes on, right? You as an individual, you get sort of faster at it if you're doing the same process over and over. And then as a company, right, you can streamline the process. You have a better understanding and gain experience in sort of the in overall aspects of production. And so you can look at learning curves of different technologies, and then this type of shape is a shape that you generally observe fairly consistently. And so you can calculate your coefficients A and B in order to determine what forecasts of production might look like for any sort of generic technology. So empirically, what does that look like? So I think we actually even saw a version of this before. But essentially, you can look at real data of deployment of different technologies. So like, solar technology, wind, electric vehicles, right? So any sort of new technology that's coming onto the market, you can look at how what the cost is per unit and how that has sort of come down as you deploy more and more of that particular technology. And we can see, right, that particular relationship of this exponential decrease, right? So this is exponential because these are growing by order of magnitude. Even though the like coefficients, the A and B of that isn't the same for all of these different technologies. It's not as though some things are going up or some things are sloping in different ways, right? We can capture all of that because the trend, the shape of the trend is the same or close to the same for all these technologies. And so that lets us take this and then extend it outwards, right, into the future. And so for consistent trends that exist in the market, in this case, we're talking about experience curves. When we see that and are able to capture that, then you have a better, you can develop better models to characterize those trends. Any questions about this? Yes.
In your opinion, why is the EIA always missed on cost targets over the past like decade?
I don't work at the EIA.
Why do you think because they miss by quite a lot?
That's why they miss it, is because he doesn't.
Yeah, exactly.
Do you think there's a specific.
they have a very hard job, and they don't miss everything, right? There are some, I think people tend to highlight when they do these retrospective analyses all the things they got wrong, but I don't often see them highlighting all the things that they got right. So typically the things that they get wrong are like energy prices that are highly nonlinear and don't conform to like trends in the past. Those are usually the things that they're getting wrong, but those are usually the things that everyone's getting wrong.
Well, I mean, like the solar, like the cost per watt of the solar, estimated like the closest organization 20 years ago was like Greenpeace, right?
Yeah. Well, so they may be, I mean, I don't know exactly what, so the EIA in the annual energy outlook, they use what's called the NEMS model. And I don't know exactly the approach that they take to do their sort of cost forecasts. If they did something like this, it'd probably be fairly accurate, but then they may be doing something like very fundamentally different. Yeah. Yes.
For the blue line, compared to everything else, the olive lines, and especially towards the end,
Here.
doesn't the relationship sort of fall apart? Variance of the error term starts to depend on the cumulative deployment. And also the error term seems like it's the expected value of it is not zero compared to all of the lines where it seems like the error term is sort of following its trajectory that's required of a linear regression model. For the blue line, it's falling apart, yet it has such a high R squared and a p-value of 3.
That was like a breakthrough.
Yeah, yeah.
Yeah. Look,
So that does not completely violate foundational principles that make a regression legitimate. That the
Like-
expect value should be 0 and towards and should vary with x, but towards the end, especially with the blue line,
No,
seems to
that's
fall apart.
no, that's not a. It is somewhat problematic, but you can do like heteroscedastic error terms. That's not really
Also,
that.
do they use robust kind of errors then? You can't
I don't know.
robust errors.
Well, but in this case, like you're saying that the error is correlated to X.
Yeah, compared to everything else where it doesn't seem to be so much.
I don't know,
it's
like that.
pretty well-
I mean, but the extent of where that's happening is like here. That's, I don't know. That doesn't seem that big to me.
Yeah, no, so that part is, I feel it doesn't, that's towards the end, it seems the relationship seems to fall apart a bit.
Your R squared is still okay, so it's like how long.
Could be inflated, could be inflated.
Yeah. I mean,
Just comparing to every other line, this one seems particularly obvious. The relationship seems to fall apart towards the higher end of the x values. Unless they did something like robust
you're using very strong language that it's like falling apart. Like, it's not that bad, dude.
relatively compared to everything else, where everything's sticking pretty close to the trend line.
I don't know. That's like, isn't like that, like that, like that. I don't know. That's
Electrolysis, that's okay.
yeah. There's like, oh, like
Yeah, that's not that great.
I don't know if I could come to that conclusion without doing some like statistical analysis, right? So
It's a log scale, that's why it's.
yeah.
Pronounced at the end.
Who knows? No, that's the beauty of this approach. Yeah. That they figured out there's this nice relationship that exists between these two things, and you don't even necessarily need to care about time. Okay, so that is one example. So specifically about how cost relates to your production and deployments. There is also, other examples of this. So we observe empirically that technologies tend to be adopted in a specific pattern. So there's like some up and down-ish things, but generally what you're seeing is this sort of S-shaped curve type thing with technology adoption. Generally, what that means is that you have this theory of technology diffusion that kind of follows this idea, right? And so at the beginning of a new technology, there are some people who will adopt it, and then you've got early adopters, early majority, and then as these things get cheaper and more popular, then you have your late majority and sort of laggards who fall in with the adoption of that technology. And so that's for sort of your new adoption events, right? And so your cumulative looks like this sigmoidal curve. And so this red line here is essentially what we are observing happening with all of these sort of different technologies. So similar to the learning curve, there is like this specific pattern that we can try and build a model on to sort of specifically look at how technologies might be adopted over time.
Well, I was just saying that in US households, more people have like TVs than they have internet. Yeah, color TV. Yeah, just even in 2005.
Internet here.
Just
Yeah.
Just like dial-up. I don't know.
8 Mbps.
You don't know that.
I know.
Yeah, I mean, that's not surprising to me.
Well, it's just like something.
Yeah, no, the cell phone one is always pretty interesting. That one, I think, is one of the fastest ones that has ever happened. Yeah. So if you have a sort of simple logistic model, you can describe that relationship. And there are just a sort of couple parameters here. So you have K, which is your saturation. That's the highest point that you will get. Growth rate, share in base year, and then this information, the year that you're in, and then your base year. So, the equation looks actually, somewhat complex, but actually, the nice thing about this is the model assumes this kind of shape. And so even if you have just a couple data points, right, you can actually see in this case, this might be a new technology that's getting adopted. With just a couple of years of data, I can essentially figure out what the rest of the adoption curve is going to look like, on the basis of this structural form, which replicates kind of all these other technologies that we see getting adopted in this way. And so the real beauty of this model is that, okay, if I know the share in my in a couple other years, and then I want to look at what the share would be in a particular year, all I need to solve for, right, essentially is my growth rate. And you have to make an assumption about your sort of saturation as well. But once you have that, then it'll sort of construct this this simple logistic curve for you. And there are some kind of specific drawbacks with the shape of this curve. It's the shape of it is a little bit more set in stone. And there's essentially like a sort of constant growth rate for the technology when you assume this type of model. And so there are sort of more complex versions of this. Yeah. EXP is exponents, or it's like e to the whatever. number. So it's the inverse of natural log. Yeah. Yes.
When you're the max penetration, how will your model, or how might this change based on the estimates? An example of like, there's always like, at a certain point, if you hit X percentage of saturation in the market, this technology is going to take over. Like electric vehicles, electric vehicles need to get to 25%. I'm making up a number for instance, right? But if you get to there, then it's like, it's going to run away. Is that,
Yeah.
can you assess that out? I mean, you're kind of guessing that you're making assumptions that's
Yeah. So there's a couple different, like if you go back to the, to this thing, you know, the runway, I don't know where you would necessarily define that, right? But like, you know, there's a inflection point that happens at 50%, right? And so that's the steepest part of your slope. So maybe that's what you're considering as like your runaway. Yeah, so with a logistic model, that's always going to be at 50%. But then sometimes you might want a slightly different curve. And we'll show how to do that in a second. Yeah, so the idea is that, okay, not everything might look exactly like that S-shaped curve that's formed in exactly that way, where you have the inflection point at 50% and with the symmetry in the early and later. And then you can actually observe that happening in a couple different sort of technologies. And so these still kind of look like S-shaped curves, but then they're the equivalent, this part of the new adoption events doesn't necessarily look normal. And so there are other sort of more complex diffusion models that try to account for this, or at least try to introduce sort of flexibility in the way that the shapes are formed. So one example of this is a Bass diffusion model. And the idea, the like concept of it is kind of like you have these innovators and you have imitators, and each of those have like coefficients associated with them. I always felt like that was like a little weird. I think the coefficients essentially are describing like characteristics of the shape. That lets it be more flexible than a simple logistic curve. So that normal distribution shape that we were talking about will look something like this. But then your imitators and innovators, like the shape of these can be sort of adjusted a lot. And so that lets you sort of make your S-shaped curve more flexible. So the inflection point doesn't have to be at 50%. It doesn't have to be symmetrical. It can be sort of more sort of nuanced and calibrated to the data. So the equations look something like this. And again, these are fundamentally just regressions. These are regression equations where you are trying to solve for your P and Qs. And you have data, you can have a series of data telling you the cumulative amount or the annual sales of something. And so you would have a vector of n's, right? So n in year 1, n in year 2, n in year 3. And you would essentially use that to solve for your P and Qs. So it's just like a slightly more complex regression form. And so this would not be a regression that has an analytical solution. You would just use some numeric algorithm to solve for your P's and Q's, which are equivalent to the betas in your linear. It's just describing this shape instead of a straight line. Yeah, so this is cumulative sales, and this is your annual sales.
And there's S curve, big M's S curve, little M's.
Yes.
Does that help?
Yeah, so this is annual and this is cumulative. Yeah. So you can see in this particular example, it has morphed my S shape into this curve. Yeah.
And assuming the answer is there any, there's a relationship between the two, but is there the ability to take the area in between them to assess the amount of, the amount of time or the additional, is there anything you can manipulate those two, the relationship you want to find something interesting about how much time, how much longer it may take, or
Yeah, definitely.
other probabilities or
Yeah, so you could actually look at empirical examples of people who have applied the Bass diffusion curve to other technologies, and they might have different values of P and Q, and you can see how that changes the shape. And sometimes it means they have like a long runway before they take off. Sometimes it means something like this, where your highest adoption is actually right at the beginning and then it slopes off at the end. So like there's a lot of variations of P and Q that you can sort of manipulate to change the shape of your S-shaped curve.
Yeah, but there's nothing that like the little sliver between the blue and green line on the left side.
Oh no, you shouldn't pay attention to that because these are no. These yeah. This is actually I do. You see this a lot, but this is on my slides. But this is a pet peeve of mine. You should never do two axes graphs. Do as I say, not as I do. Yes.
Is there any way to calibrate this model, take into account the bimodal sort of distribution for annual adoption rate? So let's say a technology takes off initially, tanks, then takes off again. So it's a bimodal.
No, that's the point. That is actually, so that's the whole point of this example, of this set of examples. No. It's not that you can't do it, but the whole reason why the diffusion models were generated in the first place is because we don't really observe that happening in the real world, which lets us make these types of models to try and encompass like the actual trends that we see. So like here, like you don't, okay, like there's this a little bit, but it's not, but you never really observe like these types of things happening. We're going, yeah, I mean,
Maybe a bimodal.
it's not, yeah.
But even over a good enough time frame, you can notice that. So for example, a technology that has an initial height, then tanks, then takes up again. VR. Yeah. And so you
No, I would disagree with that. That there is this stuff that happens, which there are like weird nuances of technology adoption, right? That happen for specific reasons with specific contexts, right? Like there must have been something happening here. There must have been happening something here. Yeah, exactly. So when yeah, okay. But hang on. So the point here is that we acknowledge there are these general trends with technology adoption, and that when you're modeling it, you're not trying to capture whatever weird nuanced Great Depression happened here, right? That's like not the point of your exercise, isn't to say, oh, I predict the technology is going to adopt like this, but there's also going to be a recession in 5 years, and therefore the technology. That's like people don't really try and do that when you're thinking about these sort of longer term forecast trends, because you're just introducing like more chances of error, right?
It seems to me like the EVs and the green energy are a little different because of the politically polarized nature in the US, right? You have, I would kind of expect that you'd have EVs peak somewhere, and then, you know, Republicans discover how great the F-150 Lightning is, and you get another upward trend.
But that's all, that's all like,
Assumptions of.
No.
yeah,
So
yeah.
This is a model for like, let's say the average tech, but you involve a factor like that or a recession. And then now that model isn't necessarily. So like there might be new models being, but not.
Yeah.
It doesn't have to be a recession. There could be the fact that, you know, the new models, let's say for EVs, are much better than the ones that came before, so the adoption rates are spikes.
But I guess the idea then is that like, but the idea is like you are basically saying that there's something fundamentally different about the technology
Yeah.
that's going to lead to a trend that would differ from all the technologies we've ever seen in the past. And it's just like, yeah, why would we do that?
I mean, we're in an unprecedented political moment, right?
Yeah, but the F-150 example, if you look at like innovators like quick fast followers, early adopters, like, well, they're probably going to be in the early, like the end of the early adopters and the late adopters, but like that's still a spike. It just depends on the time scale.
Yeah.
Right now, EV adoption.
But like, but even your example doesn't violate like the theory, right? Because like the theory is that there are sets of people who are resistant to that outcome, and we see that, right? That's captured.
Yeah.
So yeah, I mean, generally it's like so you know, it goes back to the theme of what we're talking about today. We base our forecasts off of, you know, our observations of current and past trends. And when it comes to technology adoption, like every past technology has generally followed this curve. So why would we stray from that? Okay. Yeah, last slide. So yeah, there are other models that can be used to fit diffusion processes. And so we've talked about some of these. You can include, there are like generalized versions of the vast diffusion model. So like if you want to actually introduce like weird things into your technology diffusion, like the presence of an incentive, for example, like that is possible to do in a generalized form of these models. Yeah, and there exists some work to do that. So what I'll say is that it's not totally unheard of to try and model some of the nuances of a specific technology. And there are specific variations of these models that let you do that. But generally speaking, when you're doing these types of analyses, there's enough sort of uncertainty in your forecast that adding in some of these nuances is like trying to increase precision without the ability to increase accuracy. Okay. Yeah, criticisms of these models. Yeah, so artificial restriction of the symmetry and midpoint inflections in some of the more simplistic ones, which is what has led to the development of more flexible models. Yeah, assume that diffusion processes are independent and no considerations of simultaneous diffusion of multiple innovations. So this is actually a sort of nuanced one where you could actually have sort of dependencies between two technologies that are getting adopted. And so even though the shapes are the same, you might be sort of calibrating them. The calibration might be less accurate. Oh, okay, so this one is kind of interesting. So they're fundamentally demand models. They don't explicitly take supply restrictions into account. And so, if the car companies all decided to stop making EVs, even though the demand might look like that in a process where the adoption is happening with that shape, if no one can buy them, then it wouldn't look like that. I think that one's a little bit more artificial because generally, right, supply is going to follow demand in some way. But there are actually some examples of where supply restrictions has led to sort of fairly inaccurate diffusion models. Diffusion models freeze the attributes of new technology at the time of introduction. Yeah, that's really talking about examples where you have like revolutionary fundamental changes in a technology that may lead to the shape changing. And so, can anyone think of an example of that? Hard drives, maybe, although you might even call like the difference between like a HDD and solid state as a different technology, maybe. So I'm actually thinking one that you might not even see here, cell phones. So the difference between a cell phone and a smartphone, right? When the iPhone came out, that may have changed the trajectory of what we call sort of a cell phone really differently. Although maybe everyone had a cell phone at that point.
Yeah.
Yeah. The iPhone, the iPhone came out in 2008, 2007. So yeah, close. Not almost everyone had a cell phone, sorry. Okay, and that's it for today. So I'm gonna stick around for a couple minutes because I wasn't able to be in person for my office hours yesterday. So if folks want to chat, happy to do that now. Otherwise, huh? Yeah, I think so. He had blood in his stool this morning, but the vet was saying it's probably okay. So we'll see.
You do all the x-rays and everything?
No, not yet. Let me stop recording.